Good morning. So in this video lecture, you are going to understand residues in complex analysis. So the coefficient of z minus a inverse in Laurent series expansion of f of z around singular point z is equal to a is called residue of fz at z is equal to a. So since we know that about A, fz can be expanded using Laurent series and fz is equal to a0 plus a1 z minus a plus a2 z minus a square and so on up to infinity plus a subscript minus 1 z minus a inverse plus a subscript minus 2 z minus a to the power minus 2 and so on up to infinity, where an can be calculated using formula 1 upon 2 pi I into integration of fz upon z minus a to the power n plus 1 with respect to z along the curve C. So, in this expansion, the coefficient of z minus a inverse, which is equal to a subscript minus 1. This is known as residue of fz at z is equal to a, and it is also denoted as residue of fa. So, to calculate a subscript minus 1 in this formula, we have to put n is equal to minus 1 to get the residue at fa. So residue of fz at z is equal to a, which is equal to residue of fa is equal to a subscript minus 1. And by this formula, if we put n is equal to minus 1, it will be 1 upon 2 pi I integration of fz, and the denominator will be 1. How? If we put n is equal to minus 1, it will be z to the minus a to the power 0, which is 1. So it is 1 upon 2 pi I into integration of fz dz along the curve. So to evaluate this integration, to evaluate fz dz along the curve C, we can use the formula 2 pi I into residue of fa. Next, we will see residue theorem. Residue theorem is very important theorem in complex integration. So let's see what residue theorem says. If fz is analytic in a closed curve C, except at finite number of singular points. You remember singular points are also known as poles. So if fz is analytic within closed curve C except finite number of singular points within the curve C, then according to residue theorem, integration of fz dz along the curve C is equal to 2 pi I into sum of all the residues at those singular points or poles. So let's see by diagram. C is a closed curve and a function fz is analytic within this curve C, and it has n number of singular points or poles where the function is not analytic. So the integration of fz dz along this curve C will be calculated using the formula 2 pi I into residue at f of a1 plus residue at f of a2 up to residue at f of an. Next, we will see how to calculate residues. So first method is if f of z has a simple pole of order 1. Pole of order 1 is known as simple pole. So if f of z has a simple pole at z is equal to a, then residue of f of a is equal to limit z tends to a, z minus a into fz. Let's see by an example. If fz is equal to z square upon z minus 2. To get the pole, we put denominator is equal to 0. So when we put z minus 2 is equal to 0, we have pole at 2. And since its degree is 1, z minus 2 has degree 1. Therefore, it has pole of order 1 at which point? At point 2. So pole of order 1 is also known as simple pole. So it has simple pole at z is equal to 2. Therefore, by using this formula, we can calculate residue of f of 2. So the formula is limit z tends to 2, z minus 2 into fz, and fz is what? Z square upon z minus 2. So After cancelling z minus 2, it will be limit z tends to 2 into z square, which is 4. So this is the value of residue at pole z is equal to 2. Next, if fz has pole of order n, at which point? At point z is equal to a. Then to calculate residue of f of a, we have to use the formula 1 upon factorial n minus 1, where n is the order of the pole, 1 upon factorial n minus 1 into n minus 1th derivative of z minus a to the power n into fz at point z is equal to a. So let's understand by an example. If fz is equal to z square upon z minus 1 square. So to get the pole, we have to put the denominator is equal to 0. As when we put the denominator is equal to 0, z is equal to 1. So it has pole at point 1 and its order is 2. Since the denominator is z minus 1 whole square, therefore z is equal to 1 is pole of order 2. So we have to use the formula to get the residue. The formula is pole of order n. So in place of n, we have to put 2. So residue at f1 is calculated using the formula 1 upon factorial 1 into d by dz. In place of n, we have to put 2. So it is only first derivative of z minus a to the power n, that is z minus 1 square into fz, and our fz is z square upon z minus 1 square. And we can cancel z minus 1 square and we differentiate. So the differentiation of z square will be 2z, and at which point we have to calculate it at z is equal to 1. So after differentiating, we have to place z is equal to 1. Therefore, the residue is 2. Next is, if fz is equal to phi z upon psi z, and it has pole at point A, means psi of A is equal to 0, then residue of Fa can be calculated using formula phi A upon psi dash A. For example, if fz is equal to tan z, and we have to find residue at its one of the pole, so tan z is sin z by cos z, and if we put cos z is equal to 0, it has one pole at z is equal to pi by 2. One of its pole will be pi by 2. So residue at f of pi by 2 can be calculated using this formula phi a upon psi dash a, means sin z upon differentiation of cos z at which point at z is equal to pi by 2. Since if we differentiate cos z, it will be minus sin z, and this value will be minus 1. So this is the residue of f of pi by 2. So in next video lecture, we will see some more examples of complex integration using residue formula. Thank you.